Good afternoon, everyone, and welcome to AABC's Tab Talk webinar series. I'm Colleen McCain, Marketing and Member Engagement Manager with AABC, and I'll be your moderator for today's webinar. Thanks to all our members and non-members across the community for participating today, and a special thanks to EBTRON for supporting this webinar. I have a few housekeeping notes before we get started. If you have questions for our speaker, please use the Q&A button in your Zoom window, not the chat, and we will feed those questions to our speaker at the conclusion of the presentation. You can submit questions at any time. No need to wait until the end. If you have technical issues, please use the chat box to inform the panelists and we will assist you. And finally, concerning AIA Learning Units, if you are an AABC certified TBE or TBT, please allow 7 days for your CEUs to be uploaded automatically to your portal. Today's session topic is ASHRAE Standard 62.1 and recent changes that impact the TAB community. Our expert joining us today is Darryl DeAngelis of EBTRON. Darryl has a Bachelor of Science in Marine Engineering from the Massachusetts Maritime Academy and has spent over 30 years in the HVAC industry. He currently is the Director of Business Development at EBTRON. A 20-year member of ASHRAE, he has been active in ASHRAE technical and standard committees in the development of standards and guidelines, including 11, 62.1, 90.1, 180, and 207. He is currently Vice Chair on TC 7.7 Testing and Balancing and voting member of the 62.1 Ventilation Subcommittee. I'll now be handing it over to Darryl to get us started. Take it away, Darryl.
Okay, let's see. We should be sharing now. And I see myself, and I have to laugh here because I'm looking at myself and I'm looking at this picture from my LinkedIn profile. And apparently I have to update my LinkedIn profile because I've become a lot more wiser. My hair is silver and I'm wearing glasses. So let's hope we all become wiser after this presentation. Thank you for joining me this afternoon. And for some reason, we are not starting. Give me a minute.
Darryl, were you able to take the screen? There we go. Perfect.
Okay. Yes. So you are seeing the presentation now, Colleen?
Yes, we are. Thank you.
All right. Perfect. Sorry about that. For some reason, my slides weren't advancing. Okay. So we're here to talk about ASHRAE 62. And I chose the content for this presentation based on recent changes that it may impact TAB. There are, of course, many other recent changes that are not covered in this presentation. Any published addenda for 62 is available for download on the ASHRAE.org website. And additionally, if you do not have a copy of 62.1, you can view it on the website for free. These are learning objectives. I hope I do a swell job of covering these today. And if I don't, please speak up, ask plenty of questions during this presentation, and we'll address them at the end. Okay, so ASHRAE 62 first came about in 1973, and it was known as the Standards for Natural and Mechanical Ventilation. It was modified and then reissued in 1981, and the title was changed to Ventilation for Acceptable Indoor Air Quality. I laugh at that because the ventilation rates were significantly reduced at the time. During the 70s and the early 80s, there was an energy crisis. So people were tightening up buildings and then reducing the ventilation load and as a way to save energy for operating buildings. In addition to that, there was a new procedure put into place called the IAQ Procedure. And this was an engineering-based procedure that an engineer can design a system and say, okay, this is how much air I think you need. Another interesting thing that happened is there were smoking rates back then because you could have a building that has smoking. Now, of course, it seems kind of funny to anybody that's born after 2000, but you could go to work and smoke at the same time. Interesting enough, in the late 80s and the 90s, something came about called sick building syndrome. It's curious that if that was related to the lowered ventilation rate or tightening of buildings or the smoking. But anyways, that happened, and it was quite a bit of a problem. So in 1989, when the standard was reissued again, the rates were increased by about a factor of 3. So let's fast forward to 2001. In 2001, there were some significant tab-related requirements that were put into place. There was a reference to the ASHRAE Standard 111 for ventilation of the air balance. This is the ASHRAE standard for testing and balance, if people are not aware of it, which the TC 7.7 is the cognizant technical committee above that. And there were also requirements for testing the outside damper and the related controls for that prior to occupancy. In addition to that, there was some operation and maintenance requirement to make sure that the systems were being maintained and that there was some remote monitoring or inspection of outdoor air dampers, but there was no specific frequency. It was just a suggestion that you do this. Unfortunately, the suggestions don't always take hold. These are often more neglected than not, even today. And so since 2001, the standard has been continuous maintenance with addendums produced on a regular basis, going up for public review. And every 3 years, it's published as a new consensus standard. So in 2004, there was a slight change. It went from ASHRAE 62 to 62.1 and 62.2. Now, 62.2 we're not discussing today. It's purely focused on residential, where 62.1 was focused on non-residential. It was written to code enforceable language. So this allows it to be easily adopted into local mechanical and ventilation codes. And one of the big changes is the ventilation rates. Instead of a single rate, it was broken up into a ventilation per person, per occupant, and a ventilation per building or area or per the space. This was basically important. So every space is not treated the same. Some spaces need more ventilation than other spaces because of off-gassing in that space. So there's some advantages to that. And in 2006, it was adopted into the Uniform Mechanical Code, and then through a 2007 supplement, and through the issue of the 2009 International Mechanical Code, it was now incorporating the ventilation rate procedure. So this has kept the code ventilation requirements and ASHRAE 62 closely aligned. And then in 2013, other standards such as this wonderful book here, it's not focusing because it's black, but it's the AABC National Standards is now accepted as an equal to Standard 111. And and for the first time, there was a requirement for follow-up verification after 5 years. So let's move on to more or less present day, and let's look at the code adoption. So the way the codes are adopted, they have to go through a public process and a governmental process. And typically what happens is the mechanical code lags 62.1 by at least one standard. So the latest mechanical code, for example, is the IMC 2021. It adopted 62.1 2018. But currently, we're moving on to another standard. So as you can see, the 2018 version is in purple, and earlier versions are in different colors. So basically what happens is the adoption process ends up being much slower, and some states really lag behind. And most of the states incorporate statewide, but there's a handful of states, about a dozen states, that incorporate per county or per municipality. And then some of the major cities in the US have their own ventilation code as well. One important thing to note is that the Uniform Mechanical Code or the International Mechanical Code do not incorporate 100% of 62.1. So keeping up to date with the latest of 62.1 helps ensure professional competency with indoor air quality, because we're constantly evolving the standard, adding new lessons learned, and improving upon what has been done in the past. So speaking of the past, the first change I'm going to talk about is a change to the title. This title has been the same since 1981 when it changed for ventilation for acceptable indoor air quality. However, now the new title is ventilation and acceptable indoor air quality. Although this appears insignificant, it basically reflects how the standard has evolved. Ventilation isn't the only way to maintain indoor air quality. It encompasses everything, including the design, the installation, the control in the systems, the selection and operation of the right components in the systems, and then the activities such as tab, commissioning, and maintenance. So all of this makes for indoor air quality. Okay, one thing I wanted to highlight here, Section 8 is something called operation and maintenance. And people look at ASHRAE 62 as a design standard, but it really is an evergreen standard. It's going to be everlasting. So a building should be designed to it, it should be built to it, and it should be operated to it. Otherwise, you're not going to maintain the minimum flow rates or the indoor air quality that it sets forth to achieve. So this particular task that I've highlighted here is an important one, where it's talking about maintaining airflow sensors, anything that had to do with operation of the outside air. And so that could be a flow sensor. And of course, a flow sensor that's sitting out in the outside air is going to be subjected to pollen and dirt and soot and anything else, just like any other component or the filter or pre-filter. That's why we do have filters. Pressure transducers and other sensors. Pressure transducers are going to drift. The extent of the drift is going to depend on the original accuracy, the span of the transducer, the environment it's in. A pressure transducer outside, because of the extreme temperature ranges, is going to drift a lot faster than pressure transducer inside. And CO2 sensors, for example, CO2 sensors are responsible for demand control ventilation. And although most of them have background calibration these days, their calibration is to a single fixed point, typically 400 parts per million. And they are also affected by temperature and pressure. So these things have to be calibrated on a regular basis. There's another thing here talking about verifying outdoor air. Well, of course, this is the most important thing. It's the foundation to make sure that we have good indoor air qualities and ensure that we have the right ventilation coming into the building. So why would the outdoor air fail? Well, you have degradation of the mechanical components. You have actuators that can break or slip. You have linkages that can break as well. And of course, we found out during COVID, there's a lot of deferred maintenance. And that was one of the challenges that systems weren't performing as they were because they weren't treating this document as an evergreen document and keeping it up. So what I'm saying to all you listening today, this should be reoccurring revenue for tab and commissioning companies. The standard is saying, you must do this, you shall do this. And you should be going out selling your services and saying, hey, we got to verify it to make sure things are going well. So when the next pandemic comes around, the systems are ready. Okay, so they're ready for a poll question. And I can't wait to see what the answer to this is. There should be some background music, but I don't hear anything. Do we have an answer yet? Okay, well, that's good. So 50% or more times we have trouble getting to adequately balancing the outside air, which is the case, and that's what we're going to talk about right now. So one of these important changes, which to you on the call would think is obvious, is not. And so this is an important change for the industry to ensure that designers and manufacturers provide suitable access to allow not only for good air profile, so that the balancer can get in there and actually do his job. Make sure that he's not bypassing the airflow or blocking the airflow as it's going in, and to make sure that we can actually set it. I mean, we're not miracle workers out here trying to set the flow rates. So it's important for all of us to impress on everybody that's responsible, whether it be the installers, the manufacturers, engineers, or designers, that this is in the standard and it's an important thing to follow. Another thing I'd like to discuss here, and since the poll question happened, it didn't advance. Okay, is in 90.1, which is the energy standard in 2014, manufacturers started producing equipment to reflect a change, which was to have variable speed, constant volume equipment, or they referred to as multi-speed constant volume. So really, in commercial equipment, there's really no such thing as constant volume equipment. They'll refer to constant volume all the time. And what this means is the speed is always changing with the load. So as we approach the temperature in the space, with modes of operation, such as cooling, heating, or ventilation. And this constantly is changing the balance point to maintain the same ventilation rate. Because as the supply air turns down, the mixing box, for example, is going to be less negative, which is going to have problems bringing in more outside air. So you have to open up the outside damper more to compensate for that less mixed air pressure capability. So all systems are pretty much acting as VAV systems, whether they have a terminal box or not, and they need to be balanced as such. Another thing, an important thing to note is, of course, this is going to affect room air distribution too. As you're turning down the supply air, some diffusers may dump, you're not having the air changes that you would normally. We talk about air changes during COVID and everything else. So it's another thing to consider. This is to meet energy standards and energy codes. So basically what I'm saying is you can no longer have a fixed damper, a fixed opening, because you have dynamic systems and it's changing. So you have to have a modulating damper, you have to have logic, and this logic has to be closed loop control. Otherwise, you're not going to maintain the minimum flow rates that you need to. In addition to that, demand control ventilation requirements have significantly increased over the last 20 years. And this is making conflicting control. So for example, if the temperature is coming close to the set point in the space and the requirement is that the fan speed turn down, and all of a sudden people start leaving the space at the time, so that the damper wants to start opening because the fan speed is turning down, but now people are leaving the space, so the damper wants to start resetting back because there's less people in the space and you need to ventilate for fewer people. So that's the challenge that we have. So controls need to be much smarter. We have to make sure that we test systems to make sure they are performing that way. So whether it's an RTU, a fan coil unit, or a DOAS unit, whether it's single zone or multi-zone, they're all providing variable supply air, and we need to ensure that we're meeting the current occupant minimum ventilation for that space. So natural ventilation, I bet you wouldn't guess that I was going to talk about natural ventilation on this presentation, but there has been some recent significant changes to natural ventilation that impacts this community. So first of all, I just want to say, regardless of whether it is natural or mechanical, there's a new requirement that the outdoor air should be okay. You want to make sure that you're not making the indoor air worse by bringing outside air, so that's, in some places, maybe natural ventilation doesn't work. And if you're using mechanical ventilation, then you have to have special filtration, maybe carbon filtration or other means to treat the air. And speaking of that, there is now a requirement for integration with mechanical ventilation. There are some exceptions to this. But why would you want to integrate with mechanical ventilation? Well, the wind doesn't always blow. And some areas, it's very windy, maybe the Windy City or San Francisco and other places, but not 100% of the time. So you may not have the pressure forces needed to get the right ventilation amount in there. And in other cases, openings may be adjustable. If someone has the ability to close the opening, then obviously you're not going to get the right amount of fresh air. If they're variable, perhaps it's not at the right setting point that it should be. So you want to make sure that you're providing the same minimum ventilation, regardless of whether it's mechanical or natural. So we're going to start seeing more hybrid systems, and this should have more tab involvement. Another interesting thing is this now prescriptions for the opening sizes for natural ventilation and the location. It makes sense, right? A certain size opening is going to produce a certain amount of outside air into a space. And there's also new limits on the distance from that opening that you're allowed to provide with that natural ventilation, which also affects the ceiling height, because as the ceiling height increases, the volume of the space increases, and you have to have more outside air to mix in with that indoor space. So, and an additional thing, if you do not follow the prescriptive requirement and you have an engineered system, then the engineer must show his calculations on design documents, and then more importantly, the control methods of how he's going to maintain that. So if you are going to have operable openings for natural ventilation. You have to show that the controls are going to open them whenever the space is occupied, and so forth. So bottom line, again, there should be more tab involvement in these systems. So here's another thing that I think is fairly obvious, and that's exhaust system and exhaust pressurization. Air should always flow from some place that's clean to some place that's less clean in order to dilute. And you should provide exhaust in areas where you don't have enough fresh air ventilation for that dilution. So a perfect example is a bathroom or a restroom. I have, for one, have been in a lot of restrooms and a lot of buildings that are either too hot or too cold. And I don't know how to say this correctly, but the air is not so nice. So the air is not being exhausted and diluted as it should be. Many designers perhaps do not realize that the difference in the airflow supplied to the airflow exhausted actually creates the pressurization. This is known as the pressurization flow. So simply put, you have more air exhausted out of a space than supplied to the space, then you have a negative pressure space. But let's take consideration. So we have a lot of exhaust fans now, especially like in restrooms and other spaces that are tied to light switches or occupancy sensors. Well, so that doesn't turn on until someone occupies a space. And then you have supply fans that are variable. They may be one speed or another speed. So you have a really dynamic system. You have exhaust turning on and off, you have supply turning on and off. So it's a lot more complex than you think to maintain that negative pressure. And you have spillage of air and you don't have the right amount of exhaust, and you have, air that's not so good. So this requirement is to ensure that you're going to have a negative exhaust pressurization, and then you have the controls to do that. So you see on hospital drawings, you see on laboratory drawings, you see pressure and flow diagrams. I'm a proponent of seeing these on all mechanical systems, because you have to understand the buildings are very complex. The building itself is a living system. You're going to have stack pressure. You're going to have doors opening and closing. You're going to have mechanical systems with variable speed. So there's a lot of dynamics going on. And if you have flow diagrams showing what's happening, then you have a better chance of making sure it happens in reality. And these are things that are all hard to test all the time, right? So energy recovery, it's an important thing today to recover as much energy as possible. So ASHRAE 62 actually allows the energy recovery from janitor closets, from bathrooms, as I just mentioned, from trash rooms, from animal spaces. But again, the object is not to return the odors in the air back to other spaces. And one important thing about energy recovery is, there is always a little bit of leakage. It's called exhaust air transfer ratio. And the allowance for this leakage has been around for quite a while, a few versions of this standard. However, there's a new clarification in this addendum that this leakage now does not count as ventilation air because it is tainted air. Thereby, when you're balancing, your balance better be on the high side on the total outside and the outside airflow, because you can't count that 10%. So you don't want to be balancing exactly with that respect to that. There's another addendum I don't cover into this about separation distances, like you have an exit louver, an exhaust louver, and an intake louver that are close by. You have to have a minimum distance there. It's the same idea. The idea is not to ventilate with return air, right? It's to ventilate with outside air, which we assume is going to be better. Okay. So talking about better air, I had mentioned that the IAQ procedure has existed since 1981, and this is another engineered system. However, there hasn't been many prescriptive requirements with respect to the system. So ASHRAE has been taking a look at this for the last 6 years at least, and really taking a hard look and working with the industry, because it's a consensus standard, to come up with a way to make it better. Because one of the challenges is as it was in 1981, today, there is the trend to say that, well, if I use the IAQ procedure, then I can reduce the amount of outside air that you would have in a ventilation rate procedure to save energy. So people sell this as an energy saving method. as opposed to, a source cancellation method, or ventilating for a specific compound that's in the air. The intent of the IAQ procedure has always been to provide the same indoor air quality that you would have with a ventilation rate procedure, but engineered a different way. Today, there are a lot more sources of chemicals. Back in 1981, there wasn't a computer on every desk. There wasn't maybe a printer on every desk. There were far less copiers. There were less products like desks and carpets and everything else. They're synthetic. They're potentially off-gassing. And people wear a lot more synthetic material clothing and sneakers and perfumes than they used to in the past. Certainly, we don't have the smoking, but there's a lot of things that you can't see. The challenge with air is most of the things in the air you can't smell and you can't taste. Certainly, if someone had garlic for lunch, you're going to notice that, or if someone's a smoker, you may notice that. But most of the things you do not feel. And this was a challenge that we had with COVID. It was easy to pass from one person to another because you couldn't see it and you couldn't feel it and you couldn't taste it. So you want to make sure that when you're ventilating a space that you are ventilating well. And there's a lot of products that say they clean, disrupt, or treat the air. However, the industry has been lagging behind a little bit with standards and certifications or third-party testing for these products. So we're trying to catch up and we're trying to be careful. One of the terms I heard about during COVID was rebreathed air or shared air, and we want to make sure again what we're rebreathing or sharing is not this bad air. So there were two new definitions that were added with this addendum, and it was talking about particulate matter, and particulate matter 2.5. That's really small stuff that get deep in the lungs and really cause problems in your life, like as it sits there and builds up. And then there's design compounds that can react with other things in the air or react inside your body. So there's these definitions, and there are limits that are set, and ASHRAE didn't make up their own limits. There are industry limits that already existed that ASHRAE is borrowing to establish. So someone that's going to use this engineered system now has to look at these design compounds and determine what they are. And they have to do a mass balance calculation. This basically means that, okay, so you expect that you have one of these compounds in this air. And so you say, how much is this compound being generated? How much outside air do I need to dilute that? That's your mass balance calculation. So they have to do that. And so the engineer also has to show this calculation, and they have to show these design compounds on the drawing. Again, the ventilation rate procedure is based on what they call usual stuff that's in the air. So unusual substances or unusual things that are unusual sources in the air are these design compounds. And so you have a different procedure to handle that. So you have different engineering requirements. An interesting thing that they're doing now in this standard is requiring a subjective test afterwards, asking the occupants, does the air seem good to you? I hope so when you engineer the system this way, that it's going to. But furthermore important, there's going to be a test requirement, a post-occupancy test requirement, and it's very prescriptive as far as the test duration, the equipment that's used, and the methods that you use to determine this. So if an engineer is using this method, he better ensure that he doesn't undersize the system and can't go backwards because if for some reason he fails the test more than once and wants to increase the outside air, but the ductwork was sized for less air or the equipment was sized for less air, it's going to be a challenge going backwards. So something to consider. It's an important thing. So now switch a little bit and talk about density. This addendum is still in process, but it's very important, and it shouldn't be. It's actually been in the standard for a while, but this addendum, the way it's written, is trying to make it more explicit that there needs to be a ventilation rate correction. TAB personnel are used to making density corrections. Engineers typically have this done in an automated load calculation software or selection software for a fan or other components. However, when it comes to ventilation, engineers typically aren't making the correction. Well, let's discuss about why this is important. So density impacts on ventilation is due to the fact that ventilation's purpose is to dilute. And the way it dilutes is dilutes with a mass volume of air. Okay, and density impacts this mass volume. And the table ventilation rate procedure table in ASHRAE Standard 62 at table 6.1 is based on mass airflow at standard conditions that are listed here. So if you take this table and you apply it, for example, to Myrtle Beach, it applies well because it's at sea level and it's at 1 atmosphere, assuming the same temperature. And so the engineer doesn't have to correct for this. And it's perfect. However, any elevation change there above, there should be an engineering correction for, because the ventilation will then be under what is expected of the standard. And this is a minimum standard. This is a minimum ventilation. And TAB is only going to balance to what's on the design documents. They're not going to say, hey, you guys are doing it wrong. No, that's what it is. So let's take a look, as the elevation increases, what is the impact? You can see, we look at Charlotte, that's only 800 feet up. There's already a 3% deficit. And, we're given plus or minus 10% in the balancing committee to balance it. You go to Colorado and Denver, and it's, you're already 20% in the hole. Well, throw that 10% out of the window, right? You're already not meeting 62.1. Another thing that affects density is temperature, as I listed there. The standard conditions is 70 degrees. That the ventilation rate procedure is listed to. And as the temperature increases, you also have that effect. So what I did is I listed the design dry bulb, cooling design dry bulb temperatures for each one of these spaces, and I compounded the effect. And if you look, it's significantly worse. I have actually seen drawings, design documents in Colorado Springs that basically were 23% underventilated because they took the 62.1 rates as actual for the location without any correction. So, this is an important thing. It's about mass airflow and dilution. So I'm going to switch gears up a little bit, and even though we're still going to talk about mass airflow, because we're talking about another mass balance calculation, and that is CO2 DCV. CO2 DCV has existed and been allowed in the standard since 1989. However, there has been confusion about the appropriate level in the space to maintain since that time. The amount of CO2 that generates in the space and comes to a steady state in the space is dependent upon that generation rate. And the generation rate is based on the individuals in the space. It's based on their age, it's based on their gender, it's based on their body mass, it's based on the activity level, and it's actually based on the number of occupants and the volume of the space. So when you looked at this, there was an updated generation rate approach that was published a few years ago in the document to the right. And, it's also important to note that CO2, well, it's a lagging indicator. It lags because it has to fill up the space. You have a large volume of space. It takes longer for the CO2, the people breathing, as I'm speaking to now, and I'm pushing out CO2 to fill into that space. And as you bring ventilation into space, you're diluting the CO2 that's building up. And there's actually CO2 in the outside. It's somewhere between 350 to 450 ppm, depending where you are on the planet. And this buildup may actually take an hour or even more than an hour for it to reach steady state. And that's assuming that people don't leave or come into the space, because that changes the equation. However, so there's a direct correlation between CO2 level and ventilation. They're interdependent. And if you know the generation rate and you know the CO2 value, you can estimate the rate per person. And that's why CO2 is used, because each person generates a similar amount, but it is different. So this is an estimate, and it's certainly not a direct measurement of airflow. And here's the magic number. Not all spaces are 1,000 parts per million, but this is what I see on many design documents. So I'm going to ask another poll question here, and we'll see what the answer is. Drum roll. Not surprised, exactly as I expected. So let's talk about the CO2 generation. All right. So steady state value, is just that. And when you look at ASHRAE 62, when 62 2004 came out, or was actually Addendum and to 62 2001, okay, they separated that occupant area ventilation rate and the area ventilation rate. So it's two different values, which really made the calculation of steady state a lot more complex than it used to be. But what I've done here on this chart is I've combined that occupant plus area rate. It's on the y-axis as CFM per person. And this curve reflects where the ventilation rates in the table 6.1 intersect on that line, and what the corresponding CO2 parts per million rate is below the steady state. So they are significantly different because there's a lot of orange dots that don't line up all on 1,000, as you notice. And you can also see that the first dot all the way to the left is for classrooms 5 to 8 years old. That completely falls off the curve because their generation rate is much different than an older teenager or an adult. And this curve that I actually drew is really specific to adults ages 30 to 60, 50-50, male, female, with a mean body mass and low activity. You're basically sitting, working at a desk, which is about 1.3 Met. It's also based on 70 degrees and sea level, because there is a temperature and a barometric. There's a density effect on CO2 as well as CO2 sensors. CO2 sensors only, well, CO2 sensor has to be adjusted for elevation, just like an airflow measurement. And, so if we take a look, what happens if we have an office, instead of people sitting at desk and they're all walking around all the time they have a higher metabolic rate, they're generating more CO2, so the curve shifts up. And you need a lot more ventilation to maintain that same 1,000 parts per million, or just maintain any of those dots along that curve. So if you look at, again, the office value, originally it was 17 CFM per person, but with people walking around, it's now about 25 CFM per person that you need. That's quite a difference. If we look at this chart over here, I've plotted basically different activity levels, different metabolic rates. So you certainly wouldn't want to take a building and design it for an office space and then populate it with a healthcare club, because you're going to be way off. You're not going to have enough air. You're going to be having, your CO2 is going to be rising up so much. So if during COVID, I've been hearing everybody saying, hey, well, just maintain 800 ppm and you're going to be all set. Well, a lot of systems aren't going to be able to do that, because an office, yeah, okay, it's only 200 ppm different. It may be able to do that, but a conference room, where a conference room by ASHRAE Standard 62 is at 2,300 parts per million, that's quite a big difference. Okay, so the addendum here, Addendum EB, has been in process for quite a while. It's almost complete. It's been out for review 4 times, and there's only one more comment that we're overcoming before it's issued. And we should come to that, because we're working with the comments around this. But the idea is to ensure that we are providing the right ventilation rate for the current occupancy, and clarify this misunderstanding that everything is not 1,000 parts per million. So we created these tables that show all the steady state values. And these steady state values, again, are based on the area rate, the occupant rate, and the occupant load in the space. And these values are also assuming 400 parts per million. Okay, so we're showing here the differential value. So if you use a different value other than 400 parts per million, it's additive. So for example, we take a theater and we use that 400 parts per million, then the steady state value is 2,500 parts per million. It's 400 plus 21 equals 2,500. If it's 300 parts per million outside, then it becomes 2,400 parts per million. But the important thing to note is, if the theater isn't fully occupied, or If the default occupancy is different, for example, the number of seats in the theater don't match the default occupancy that we have in ASHRAE 62, then the value is incorrect and additional calculations need to be made. So this is an important thing to consider. Another important thing to consider is how the sequence of operation works. I've seen so many sequences of operations that basically state, stop to modulate the outside air damper when it reaches the set point, or 1,000 parts per million. And that is incorrect. Not only is the 1,000 parts per million perhaps incorrect, but modulating once you reach that set point, well, that's a steady state. I mentioned before, it takes a long time to get steady state, perhaps an hour or more. And basically what the standard says is you should be ventilating for every occupant in the space. So the approach is you start to ventilate once the CO2 rises in the space. So if your outdoor CO2 is 400, if the CO2 is 450, 500, then you should start to be opening up the damper, and that's how the sequences should work. There are other standards out there that also say that it shouldn't operate until it reaches the steady state. Again, they're incorrect. Because the idea is we want to make sure that we always ventilate for the number of people there. And again, this is a lagging indicator. It's definitely not measuring the flow directly. And in some cases, it may make more sense to direct counting. Let's take an example of that theater or a movie theater. You know, where you have a set number of seats and you have a set number of tickets. They know what time the movie starts. They know how many tickets they sold for the movie. So they can count the number of tickets sold by the ventilation rate that's required for that space and modulate the damper to that number. Very quick and easy, instead of waiting 1 hour for the space to become steady state. So if someone were to take this theater, for example, and try to maintain 1,000 parts per million, well, guess what? You're probably going to be a CO2 alarm. Or if you don't have an alarm set, and you don't have any limits on the outside air damper, and it's going to continue to rise up in the amount of ventilation to maintain 1,000, you're going to go from 12 CFM per person all the way up to 40 CFM per person, because that's what the rate is to achieve 1,000 parts per 1,000 parts per million in that space. So how is the equipment going to perform? How is the lube going to perform? You're going to be dragging in rainwater, etc. You're going to have challenges there. All right, so, you know, as I said, you know, there's ASHRAE 62.1 isn't just a design standards, and, you know, it isn't just for, you know, designing a new building. We want it to be evergreen and continue on. And this is new addendum that's the focus on existing buildings and trying to ensure that existing buildings, especially in light of COVID, are providing you know, good ventilation. There's a lot of lessons learned that we didn't have the control sequences, that there's a lot of deferred maintenances, and buildings weren't achieving what they thought they were achieving. So this addendum here is trying to ensure that, you know, hey, this gives you a way to check on, you know, how to ventilate for existing buildings. However, you know, complying with the most recent version of the standard may be a lot different than complying with the standard that was used when the building was built. So there may be some challenges to achieve that, but, you know, trying to achieve it is what all you can do. And of course, measurement. You know, you all have to can go out there and measure and verify. You know, can you actually do this? Can you actually, you know, speed up the fan and not overamp the fan and ensure that the outside air can take in enough outside air without bringing in the rainwater, etc., to get this. You know, ventilation is, again, the foundation of good indoor air quality. And finally, you know, checking the control sequences. Are things functioning correctly? Have you changed anything? Has the occupancy changed? You know, what is it should be? In my bio, I said I worked on ASHRAE guideline 111, and it's field checking of controls. It's a good start. So that's a good standard to start with as far as checking the outdoor air sequences and making sure controls are functioning and working. Because, for example, you know, actuator feedback only provides position of the actuator, not exactly position of the damper if the linkage is broken. And a CO2 sensor is only going to verify, you know, CO2 level in the space. You have to make sure that these values directly correlate with the measured value that you're performing in the field or airflow sensor that's installed in the ductwork is doing. And another change is, and this is not related to ASHRAE 62, but it's based on ASHRAE 62. So I thought it was important to bring up. And for those that don't follow ASHRAE as close as I do, this is a new guideline that's being put out, and it should be printed at the end of this year or the beginning of next year. It's already gone through, I think, 3 full public reviews. It's based on ASHRAE 62. It's mapped to ASHRAE 62 as I show with the blue and the green bars over there on the standard. And again, we talk about ASHRAE 62. ASHRAE 62 is the minimum standard. It's not the speed limit. A lot of people treat it as a speed limit. And if we start with it being the speed limit, and then we start having problems with our engine and we can't achieve the speed limit, well, then we're going to be underventilating. So this is a way to provide more ventilation and enhanced ventilation in indoor air quality. And what it does is it goes beyond, the standard and the user manual to try to achieve that. It tries to clarify that commissioning, that it starts in the design process, it goes through the design review, it goes into installation, and that we do have a good job in installation, that we are filtering the air, and that we're not using systems perhaps to condition the space that we're going to use in the future, or if we are, we're using good construction filters to capture all that dirt, and then we're not leaving rags in the ductwork, et cetera, so that tab can't do their job. And of course, with respect to tab, it's important to say, hey, it's a living document. Things happen, the occupancy changes, design assumptions may not have been correct to begin with. It should be evergreen, it should always be changing. We have the requirements to go back and verify, and that's my final point here, is it actually enhances the verification. It goes from 5-year verification on the outside air sensors to annual verification on these sensors. And it goes to verification of the outside air flow sensors from every 5 years to 2 years, because nature is that things go wrong. So this concludes my presentations, and I'm happy to take any questions you have.
Thanks, Darryl. We do have a couple questions that came in. If you just want to pop open that Q&A so you can read along. I'll read them aloud though.
Thank you.
Yep. All right. So the first question here is, why are exhaust rates in table 6-2 listed in terms of flow rate per area rather than air changes per hour?
Well, see, air changes, that's a good question. Air changes per hour, that's a challenging thing because it requires knowing the volume of the space, and the volume of the space is not set. It's easier to calculate the area of the space than that. And air change per hour, it changes from that perspective. So I guess that's the best area. And a lot of the ventilation rate is also sometimes the exhaust rate is listed, per occupant as well. For example, like, the number of toilets you have is based on the occupancy as well. I hope that answers the question.
All right. Question number 2 is CO2 DCV seems complicated. Are there other ways to do demand control ventilation?
Yeah, in my example, I think I covered one of them, and that was, you can use the point of sale system. There are things called people counters or other occupancy identifiers, certainly in Las Vegas. They want to know how many people are coming into space. So there are products for sale that you can use that are outside of CO2 DCV.
All right. Third question. Are there certain spaces, buildings that require use of IAQ procedure versus VRP?
That's a very good question. Again, the ventilation rate procedure is based on normal sources of contaminants. Certainly, COVID is not a normal source, and a lot of these design compounds may not be normal sources. So the rates in 6.1 are for these normal sources. So if you have something that's really called an unusual source or abnormal source, that would be a good time to use the IQP. If you have spaces that are unique because of the chemicals that they have or the process they have in place, that's a good time to use the IQP as opposed to ventilation rate procedure. But the standard allows you to choose which path to go.
All right, and next question. Should outdoor air sensor inspection and ventilation verification be more frequent?
It certainly will depend on the systems. Some systems may require less maintenance. One of the things that the standard refers to is look at the O&M manual, which would have the manufacturer's recommendations for a calibration. Anything that with a pressure transducer, as I mentioned, is going to drift. Thermal sensors don't drift. They're a lot more stable with respect to that.
Okay, next question. Will an OA airflow measuring station such as EBTRON is installed on a system? Does it need a density correction factor for an above sea level installation, or will it automatically compensate? Is that done at the factory, or can it be done in the field?
It depends again on the manufacturer, not to be manufacturer specific here. But the products, some of these products like a thermal sensor is based on mass flow to begin with. However, some products when they ship from the factory are volumetric flow, so they have an opportunity to change to standard airflow, and in that case, you don't have to do it. Some have automatic correction built into it. You have to enable them in the menu. But you have to really read the instructions in the setup manual to understand which product has to be set up which way. Yes.
Okay. Next question. Does 62.1 address bipolar ionization equipment?
No, it doesn't not. One thing 62.1 does address that I didn't cover in this presentation, they address ozone levels. So if there's any cleaner that generates ozone, most of these bipolar products say they do not, or they meet the requirement for ozone. They're safe. But there are different standards or guidelines that are being produced right now for testing of such products.
All right, thank you. Next question. Can we use CFM/SF for minimum outside air ventilation rates for classrooms instead of CFM per person?
Basically, when you're looking at outside air rates, you're looking at a combination too. Again, you're ventilating for the area or the building component, which is a CFM per square foot. And then you have to ventilate for the number of people. I mean, you can take the combined ventilation rate and do that, but if you're doing demand control ventilation, you always are supposed to provide, if you're during normal occupancy periods and the space is empty, you should always be ventilating for the CFM per square foot. And as people come into this space, then you're ventilating for the people as well. So it's a combined rate. And that's what's different than what it used to be in the past. Title 24 in California, a little bit different. They have a set rate per person, like 62 used to have. Another question?
Okay, another question. Can you explain the addenda process for 62.1?
Yes, so the addenda process is well, it's a long process. I mean, we have working groups that we get together in the standard committee, and we write the standard. Now, the idea for the change to the standard could be internally generated, but it can also be externally generated. Any one of you can submit a change proposal to the standard, to ASHRAE, and to the standard committee, and we review it and see if it makes sense. And then once we write up the language, and again, it's got to be in code enforceable language, we set it up for public review process. And sometimes this takes multiple reviews, and we work with commenters on this to come to consensus, and then it goes through the process. Sometimes we don't always come with consensus. We have to publish aware that we haven't met everybody's need, but it's something that's done. And then it gets published as a published addenda, and it officially becomes part of the addenda. And after 3 years of this, the new addendum, the new standard is produced.
All right, thank you. Just a couple more questions here.
Sure.
Is 62.1 addendum CO2 steady state publicly available?
You may find it somewhere out there. It's the addenda closed on that in May. So that was the fourth addendum on that. It's likely it's going to go up for a fifth addendum again, because it's has one commenter that we're working with to resolve. But each time, one thing I didn't mention in the last question, each time an addenda goes out, a lot of times they go out as a second time as an ISC, which means you can only comment on the things that are underlined or the things that changed thereafter. So you can't comment on the whole addendum anywhere. That's to prevent from someone commenting on the same thing or for someone who missed the first process. So one of the things is ASHRAE publishes every Friday a document that you can get in your email on a regular basis that basically tells you what products, what addendas out for, what standards are out for public review. So you can see, and they're typically out for 30 days or 45 days or even 60 days in some cases.
Okay, last two questions here, Darryl.
Okay.
I see a lot of AFMS that provide unstable readings even when they are installed with sufficient duct lengths, etc., that the manufacturer recommends. Any troubleshooting recommendations?
Yeah, some of these products, they have the gain that you can adjust, and you can actually slow down the output of that, the iteration that you have. And that would be something you may want to do. You want to just slow down the output, and that would try to stabilize the signal. Certainly, in some areas, it's sensing what is really happening there. You have turbulence in the airstream, and unfortunately, manufacturers try to do their best with installation guidelines, but as the TAB committee knows well, it's very challenging to get measurements, and even the straightest of ducts sometimes.
All right, thank you. And last question.
Mm-hmm.
Is there a time we can reduce ventilation to 0 with DCB?
That's a good question. There is a allowance in 62 for unoccupied or occupied shut off, and that allows a space during normally occupied periods to go to complete 0. Okay, and I don't think this is my personal opinion is there's a reason why you have ventilation for the area and ventilation for the people. And that's because the area is always off gassing. If you go to 0, then you're not treating the ventilation for the space. And then when people walk into the space and you have the lag, then whatever is in that space that may be off gas and may have built up during that period of time. So you can do it. I just don't recommend it.
All right. Thanks so much, Darryl.
You're welcome. Everyone have a nice day.
Yeah.
Thank you for attending today.
Yep. Thank you to EBTRON again for supporting this webinar, as well as our presenter, Darryl, for lending us his time today. And don't forget to take AABC with you on site with the free AABC Tab Calculator app. Access over 10 turnkey equations, a scientific calculator, and a resource library directly from your Android or Apple device anywhere. Download it now using the QR code seen on your screen or by searching the App Store for AABC Tab Calculator. Thanks, everyone, and we'll see you again at the next AABC Tab Talk webinar. Have a good evening, everybody.